Okay, the title is today's title is Morse theory and Floer theory, and I'm Masaki Taniguchi. I have been working on the Riken items from this April. I'm a mathematician working on the mathematical study of gauge theory and its applications to differential topology. The differential topology is a field of topology. Okay, so let's start the talk. Yeah, today I would like to explain what is a Morse theory. So Morse theory is mainly appeared in a topology. It has been studied from 1929 by Morse, and Morse theory provides a topological method to decompose a good space into elementary parts. So today I would like to explain the main idea of Morse theory. So in order to explain the main idea, we fix an example of good space. So for the example, we fix surface of a donut shape. Okay. This mathematically it is called the two-dimensional torus, and this is an example of two-dimensional manifold. But today I would do not explain the notion of manifold. So we fix such shape like this. Okay, so this is the first step. In the next step, we fix a nice height function of the surface. So this is a correspondence from the all points of the surface to the real numbers. So if this function has nice property, it is called a Morse function in Morse. So if suppose we have the following function. For example, if we for this point we associate a real number 2. Yeah, suppose we fix such function, and for such function f, and fix a real number r, then we can define, we consider the following subset of MR, subset of surface, which is defined by all points whose values of this function is smaller than or equal to r. Okay. For example, if we fix a real number like this, then the MR is given by the following picture, this set. So all these points has the value of f smaller than or equal to r. And this gives a sequence of subspace of a donut surface. And if r is equal to 3, then MR coincide with the total of donuts. And r is equal to -3, then we have just a point. So we fix such function on the surface. So this is the second step. And for the third step, we observe this sequence of subspace while increasing the parameter r. So suppose that r is smaller than -3, then we have nothing. So MR is empty. If r is equal to -3, we have just a point, like this. And when r is greater than -3 and smaller than -1, then we have this shape, this cap. And actually, for example, m minus 2.5 is this, and m minus 2 is this. So the size of this cap are different, but in a study of topology, we identify this space with this space. So in the study of topology, if we have continuous deformation from this space to this space, then we identify with this. So actually, we can construct the continuous deformation from this to this. So in the study of topology, we identify these two spaces. But this, for example, this changes includes this has topological changes. Okay. So, and in the next step, if R is equal to -1, then we have this shape. And if R is greater than -1 and smaller than 1, we have MR as a half of donuts. And when R is equal to 1, we have this picture. And if R is greater than 1 and smaller than 3, then we have a punctured donut. And if R is greater than 3, then we have a donut itself. Okay, so this is the observation of sequence of species MR. And next, in the next, we observe the changes of MR by increasing the parameter R. So what is the difference between step 1 and step 3? So this cap topologically same as in order to explain the difference between these two species, we take the continuous deformation from this to this. Okay, so this is just a two-dimensional disk. So disk. So by using this disk, we can describe the difference between these two species by adding this two-dimensional disk. So this is called a zero-hander in Morse theory. Okay. So this is the difference between 1 and 3. And what is the next? The difference between 3 and 5 is described by the following way. So first we consider the continuous deformation from this to this. And then we can see that the difference between this and this is just by adding this band. Okay. So like this. So this is called a 100 in Morse theory. So as a conclusion, we can see that this deformation can be obtained by pasting these elementary parts. So this is main idea of Morse theory. So in the next step, we can also consider such kind of thing. So what is the difference between 5 and 7? So by using continuous deformation, we can identify this space with this space. And the difference can be described as by adding this band like this. So this is the difference. And the difference between 7 and 8 can be also described by adding this two-dimensional disk like this, attaching. Okay, so in summary, we can see that a donut surface is obtained by pasting these elementary parts, which are called 0-hander, 1-hander, and 2-hander. And the attaching region can be described as the red lines. So this is a main idea of Morse theory. And this observation can be generalized to any closed two-dimensional manifold. And this is a notion of good species in a study of topology, which includes these pictures. And now we are seeing a two-dimensional space, but this observation can be generalized to for any n-dimensional good space, n-dimensional manifold. So this is main idea of Morse theory. Next, I would like to explain what is Floer theory. Actually, I mainly studying Floer theory. So Floer theory has been studied from 1987 by Floer, started by Floer. So this is, roughly speaking, this is a Morse theory for the functional from the infinite dimensional space to real numbers. And this infinite dimensional space coming from the gauge theory and symplectic geometry. And these two fields use ideas of physics from physics. As an example, if we fix three-dimensional good space, so three-dimensional manifold, for example, we can consider the third product of real number. And we consider some nice class of function on such spaces. Then we can see that this is, we consider this space as an infinite dimensional space, which having some group action, which is called gauge transformation. And we also have some Morse function, which is called chance-limit function. And by considering Morse theoretic construction, we can obtain the information of topology of three manifold. So, okay, so finally, we talk about the application of Floer theory. So by using Floer theory, we can treat the following problem. So which three-dimensional good space, three-dimensional manifold can be embedded in the four-dimensional Euclidean space smoothly? So our four-dimensional Euclidean space is just the product of the fourth product of the real numbers. And for example, by using Floer theory, we can prove the following result. Donaldson and Friedman proved the following result. So let sigma 235 be the intersection of the 0 point of this polynomial and S5. And we can see that this is a good example of three-dimensional. This is a three-dimensional good space. So this is example of three manifold. And by using Floer theory as an application of Floer theory, we can see that sigma 235 cannot be embedded in R4 smoothly. So smoothly means the differentiable, the embedding is differentiable. On the other hand, Friedman proved the sigma 235 can be embedded in topological in R4 topologically. So topologically means locally flat and continuous. So yeah, I'm interested in the difference between these the property of maps. Yeah. So this is one of the famous applications of Floer theory. So that's all of my talks. So thank you for listening.
Thank you very much, Taniguchi-san. So very clear and understandable talk. So if you have any questions, unmute yourself or raise your hand so that you can draw my attention. Any questions?
So may I ask a question?
Go ahead.
I have a question about the last example. I don't know the Friedman. Do you need to use Floer theories to prove both of the statements? I mean, unembeddable and embeddable things. I mean.
Sorry, I couldn't understand the question.
It is stated that sigma 235 cannot be embedded in R4 smoothly. And it is stated that sigma 235 can be embedded topologically.
Yeah.
And do you need Floer theories for both proofs of this statement, or do you need only? So yeah, I mean, yeah. So roughly speaking, how do you apply Floer theories to prove these things? But yeah.
Sorry, I see. So you want to know the sketch of proof?
I mean, yeah. So first thing I want to know is that do you need Floer theories for both statements?
No. For the first statement, we need a Floer theory.
Okay, you need the fair theory for only the first.
The
first statement. I see.
Yeah.
I see.
So let me follow up the question. So Floer theory states that they cannot only it's not done. So it's kind of gives you the restrictions.
Yeah. That's right.
So even without
actually,
so it doesn't say that if you can embed certain topology smoothly, so it takes another theory or another actual construction. So is there known that any space that the Floer theory doesn't decide it's actually embedded or not?
Yeah, maybe it's true. So yeah. So yeah, I think there are many examples which cannot be detected by Floer theory. So yeah. That's I think so. Yeah.
So can I ask a question? In the previous slide, just before this one, you talked about gauge theory on R3.
Yeah.
I mean, the gauge theory which I usually handle is gauge theory on R4. Is it only R3? Floer theory is applicable only for R3, or it's just an example?
So Floer theory can be defined for only 3 manifold, I think. 3 manifold. Okay. Because the disjunction function can be defined for such for 3 manifold. So trace of we should consider this function. So this function defined for three-dimensional manifold. Yeah.
I see. Okay. Thank you.
So is there any generalization to 4 dimensions or any relation to the some instanton calculations?
Yeah. For example, actually we have how to say, if we have 4-dimensional manifold, then we can consider the instanton on this 4 manifold, and using the all instanton modular space of X, and by the integration over this some differential form on this 4-dimensional modular space, then we have some invariant. This is called the Donaldson invariant. And if we cut this X by along some 3 manifold Y, then we have the 2 pieces of X, so X1, X2. Then the generalization of a Donaldson invariant for manifold with boundary lies in the Floer homology. So can be treated by Floer theory. And we can see that by using these 2 invariants of manifold with boundary, we can obtain the information of transfer invariant of X, so closed manifold. So this is an TQFT generalization of the transfer invariant. That's a relation between the instanton and this Floer theory. Yeah.
By the way, it is often said among the non-experts, dimension 3 is a very special. And if 4 are bigger, then 4 means easily generalized to any dimensions. So what is the special property of 3 dimension?
What is the special property of 3 dimension? For defining a Floer theory,
I think maybe the dimension is the greater than 4, not 3. I mean, less than 4 is kind of special, and if you think about a space of dimension greater than or equal to 5, then the theory is kind of homogeneous. I mean, what you can prove in 5-dimensional theory can be generalized relatively easily to arbitrary dimensional space of dimension greater than or equal to 6. So maybe, yeah, Masaki could explain so that the difference between these two, I mean, less than or equal to 4 and greater than or equal to 5. So that's the borderline.
Okay, so then we should ask him about the 5-dimensional or higher dimensional generalization.
For Floer theory,
related.
I think you may just
approach.
explain like something about classical differential topology, like Kirby.
Oh, I see. Yeah. Actually, for example, generalized Poincare conjecture. So this classifies the very special class of differential n-dimension manifold. So suppose n is closed to n-dimension manifold. So we can see that these are equivalent. So M and Sn is so this is a homotopy equivalent, and M and Sn is homeomorphic. And if n is greater than 5, we can by using a Morse theory, classical Morse theory for finite dimension manifold. Yeah, we can prove this result. But in dimension 4, we need this method cannot be used in the dimension 4. Smaller than or equal to 4, then we cannot use this method. So we in dimension 4 we need more difficult technique. But actually we in dimension 4 this is true. That's one reason that the differential topology whose dimension is smaller than or equal to smaller than or equal to 4 is difficult to understand.
Okay, thank you. I believe that answers Fujikawa sensei's questions perfectly. So any other questions? So I don't see any other hands raised. So let's thank the speaker again. Okay, thank you very much for the clarifying talk.
Okay.